Our first study of gases did deal with Boyle's law, Charles' law, and Gay-Lussac's law, and it had nothing to do with the amount of a gas at all. So in this lesson, we're going to look at how do we tie in Avogadro's hypothesis to figure out how many moles of a gas are present. Well, for Avogadro's hypothesis, since we're dealing with ideal gases, we can have hydrogen, nitrogen, and oxygen. They are different in terms of their masses. Hydrogen is about 2 grams, nitrogen's 14, and oxygen is about 32. Well, nitrogen would be twice that, which would be 28. So their masses are different. But because they're ideal gases, the size of their particles are very, very, very small. So Avogadro hypothesized if gases are at the same temperature and pressure, they will all occupy the same volume. And then, of course, we all know about his famous number, the mole, the 6.02 times 10 to the 23rd. Okay, now the key idea here is that if we look at the volume of a gas, we'll know basically how many moles there are in that gas. How is that possible? Well, let's take a look at a standard volume. A standard volume is 22.4 liters. So what does that mean? If we're at standard temperature and pressure, we know based on Avogadro's principle what volume that would occupy. And it doesn't matter what gas it is. Now, what is standard temperature and pressure? And again, we give the letters STP for that, standard temperature and pressure. The standard temperature is going to be 273 Kelvin, which is equivalent to 0 degrees Celsius. And the pressure is equal to 1 atmosphere. Okay, you can also have it equal to 101.3 kilopascals, which is also standard pressure as well. These are the two most common units that we are going to be using, okay, for the pressure, and this is what we have to use for temperature, Kelvin. You guys know that already. So if we know the volume of the gas and the temperature of the gas, we can then know how many moles there are. Well, if we're at standard temperature and pressure, we know that 1 mole will always equal 22.4 liters. So 1 mole of any gas, let's write that 1 mole, is always going to equal 22.4 liters. But we have to be at the special condition of being at standard temperature and pressure. Let's try 2 examples to see how we can apply this. An ideal gas has a volume of 45 liters at STP. Determine the number of moles of this gas. So as long as we're at STP, then all I have to do is say 45.0 liters, and then times 1 mole, and we don't know what the gas is, it really doesn't matter, divided by 22.4 liters. Okay, that's all we have to do, that quick ratio. And this turns out to be 2.0 moles of the gas, rounded to the 10th place. Now what about an ideal gas sample has 1.5 moles at STP, determine the volume. Then all I have to do is say 1.5 moles, and times that by 22.4 liters over 1 mole. And again, it really doesn't matter what kind of gas you've got. And that's going to equal 33.6 liters. So it's really easy to do this. Very, very easy if you're at STP. So the question, of course, in your minds would be, what if we're not at STP? Well, that's what the ideal gas law is for. It's pressure times volume equals N times R times T. Let's see what each of these variables are. Pressure, of course, is P, V is volume, N is now going to be moles. R is a proportionality constant that will convert us to the new temperature and pressures that we're given. Now we actually have 2 R values. If we're in atmospheres for pressure, your R is going to be 0.08206. Now I usually use 0.0821 rounded to 3 significant digits. But what if we're not in atmospheres? Another pressure is kilopascals, which is very commonly used. Okay, the R value is then going to be 8.31. So there's 2 different R values. So you do have to pay attention to if you're in kilopascals or if you are in atmospheres. And T, of course, is for temperature. Now the ideal gas law and Avogadro's principle really we're talking about if our pressures are in like 1 or 2 atmospheres at most, because that's where your ideal gases are actually. They're under low pressures. Okay, let's take a look at some examples of the ideal gas equation. Now remember, the ideal gas law, the only purpose of it is what if you're not at standard temperature and pressure? Here it goes. A gas has a pressure of 1.5 atmospheres, a volume of 13.5 liters, and a temperature of 350 Kelvin. Determine the moles. So I'm just going to make a simple chart. Pressure is going to be 1.5, and I'm going to write that as atmospheres. And then volume is equal to 13.5 liters. Notice I'm writing all my units right now. N is going to equal, in this case, we don't know, so I'll put a question mark for that one. The R constant, well, I'm in atmosphere, so I'm going to use 0.0821. And my temperature, again, must be in Kelvin, and it's already in Kelvin, so that's really nice, so 350 K. Notice how, since I'm in Kelvin, I do not need to add the 273. So now I'm going to set up my equation. The equation, again, PV equals nRT. I'm going to plug numbers into it and just solve for n. So I'm going to have 1.5. I'll multiply that by my volume of 13.5 equals n is my variable I'm trying to solve for. So times 0.0821 and then times by 350. Okay, now I need to get n all by itself. So what am I going to do? I'm going to divide both sides by 0.0821 times 350. So I'll divide this. And I'm going to write this how you're going to do it in your calculator. So parenthesis 0.0821, and I'll hit the times button. And then 350, close the parentheses. So this, of course, crosses off to be 1. And then my n is going to be 1.5 times 13.5 divided by parenthesis 0.0821 times 350, close parenthesis. And my answer comes out to be 0.7 moles. Okay, for this example, and you can say n equals if you'd like to. So 0.7 moles rounded to 1 significant, or 1 to the 10th place. Okay, let's try another question. A gas has a pressure of 104 kilopascals, so I'm just going to start my list. Pressure is equal to 104, and I'm going to label that as kPa right away. A temperature of 300 Kelvin, I'll put my T down here. 300, again, we're in Kelvin, do not have to add my 273. I have 1.4 moles, so I'm going to put N right here equals 1.4 moles. Okay, and I'm in kilopascals, so I'm now going to choose R to be the 8.31. So again, I have to pay attention to what kind of pressure I am in. Determine the volume. So volume is going to be my question mark. So again, my equation PV equals nRT. Pressure is going to be 104. Volume is my question mark, so I'll just leave that the letter V equals 1.4 times 8.31. And then times by 300. Okay, now I need to get volume by itself. Let me change colors again. So I'm going to divide both sides by 104. I don't need a parenthesis this time because I'm just dividing by one number. So I'll divide this by 104. And my volume is going to be 1.4 times 8.31 times 300 divided by 104. And that comes out to be 33.6 liters. Okay, so you might be asking the question then, so what about our units for this? Well, you might notice that pressure has two choices, and that's going to be atmospheres and kilopascals. And then your R is going to change, depending which one you use. Volume will always be in liters. So if you're not given liters, you must convert it into liters before you use it. Temperature always has to be in Kelvin. And of course, N is always moles, so we don't have to worry about anything else other than moles. So that's how we handle volumes of gases and how we get them into moles, both at standard temperature and pressure, and when we're not at standard temperature and pressure. Hope that makes sense. We're going to try a little review game to check your understanding of that.